All right, so today we have Emmanuel Ameisen. He works at Anthropic on interpretability research, and he also authored an O'Reilly book called Building Machine Learning Powered Applications. So, welcome to the podcast, Emmanuel.
Thanks, man. Glad to be here.
So, as I go through what you and your team do, it's almost like biology, right? So, you're studying these models, but increasingly they look like biological systems. So, why do you think that's useful as an analogy? And am I actually accurate in kind of calling this out?
Yeah, I think that's right. So, our team's mandate is to basically understand how the models work, right? And one fact about language models is that they're not really written like a program, where somebody's sort of by hand described, what should happen in that logical branch or this logical branch. Really, the way we think about it is they're grown. But what that means is, they're trained over a large data set, and on that data set, they learn to sort of adjust their parameters. They have many parameters, often billions, in order to perform well. And so the result of that is that when you get the model, the trained model back, it's sort of unclear to you how that model does what it does because all you've done to create it is sort of, show it tasks and have it improve at how it does these tasks. And so it feels similar to biology. I think the analogy is apt because for analyzing this, you kind of resort to the tools that you would use in that context where you know, you try to look inside the model, see which parts seem to light up in different contexts. You poke and prod at different parts to try to see, I think this part of the model does this. If I just turn it off, does the model stop doing the thing that I think it's doing? And so that, is very much not what you would do in most cases if you were analyzing a program, but it is what you would do if you're trying to understand, how a mouse works.
You and your team have kind of discovered surprising ways as to how these models do problem solving, the strategies they employ. So, what are some examples of these kind of surprising problem solving patterns?
Yeah. We've spent a bunch of time studying these models, and I guess I should say whether it's surprising or not kind of depends on what you were expecting. So maybe there's a few ways in which they're surprising. I think there's you know various bits of common knowledge about, for example, how models predict one token at a time. And it turns out if you actually kind of look inside the model and try to see how it's sort of doing its job of predicting text, you'll find that actually a lot of the time it's predicting multiple tokens at a time. It's sort of like deciding what it's going to say, in a few tokens and presumably in a few sentences to sort of decide what it says now. And so, that might be surprising to people who have heard that these are, predicting one token at a time. Maybe another one that's sort of interesting to people is that if you look inside these models and you try to sort of understand, what they represent in their neurons, they have artificial neurons, you'll find that there's sort of general concepts that they represent. So one example I like is, you can say, let's say somebody is tall, and then inside the model you can find neurons actuating for the concept of something being tall, and you can sort of have them all read the same text, but translated, in French, quelqu'un est grand. And then you'll find that sort of the same neurons that represent the concept of somebody being tall are active. So you have these concepts that are shared across languages and that the model represents in one way, which is kind of, again, maybe surprising, maybe not. Not surprising in the sense that that's clearly the optimal thing to do, or that's the way that, you don't want to repeat all of your concepts. Like in your brain, you don't want to have a separate French brain and English brain, ideally. But surprising if you think that, these models are mostly doing pattern matching, then it is surprising that when they're sort of processing English text or French text, they're actually sort of using the same representations rather than sort of leveraging different patterns.
So, is there, Emmanuel, is there a difference? So, the things you just described, is there a material difference between the reasoning and non reasoning models?
We haven't studied that in depth. I will say that the thing that's interesting about reasoning models, and maybe just to say it, is sort of these models that when you ask them a question, instead of answering right away for a while, they kind of write some text, thinking through the problem, saying, oftentimes they're used in math or code, trying to think, well, maybe this is the answer. Let me try to prove it. Oh no, it turns out it's wrong. And so they're they've proven to be good at a variety of tasks that models which immediately answer aren't good at. Um, and one thing that you might think if you look at reasoning models is that you could just read their reasoning and that you would understand how they think. But it turns out that one thing that we did find is that you can look at a model's reasoning that it writes down on, that it samples the text it's writing, right? Saying like, I'm now going to do this calculation. And in some cases, when, for example, the calculation is too hard, if at the same time you look inside the model's brain, inside its weights, you'll find that actually it could be lying to you. It's not at all doing the math that it says it's doing. It's just kind of doing its best guess. It's like taking a stab at it just based on either, context clues from the rest or based on like what it thinks is probably the right answer, but it's totally not doing the computation. And so one thing that we found is that you can't quite always trust the reasoning that is output by reasoning models.
Obviously, one of the frequent complaints is around hallucination. So, based on what you folks have been learning, are we getting close to I guess, much more principled, mechanistic explanation for hallucination at this point?
Yeah, I mean, I think we're making progress. We studied that in our recent paper, and I think we found something that's pretty neat, which is that so hallucinations, again, just to kind of say it, there are these cases where the model will confidently say something's wrong. You might ask the model about some person. It'll say, "Who's Emmanuel Ameisen?" And it'll be like, it's the famous basketball player or something. And so it'll say something where instead it should have said, I don't quite know. I'm not sure who you're talking about. And we looked inside sort of the model's, again, neurons while it's processing these kind of questions. And we did a simple test. We asked the model sort of, who's Michael Jordan, which it knows, and then we made up some name. We asked it, who's Michael Batkin, which it doesn't know. And if you look inside, there's something really interesting that happens, which is that there's basically these models by default, actually, because they've been trained, to try not to hallucinate. They have this default set of neurons that is just, if you ask me about anyone, I'll just say no. I'll just say, I don't know. And the way that the models actually choose to answer is if you mention somebody famous enough, like Michael Jordan, there's neurons for like, oh, this person's famous. I definitely know them that activate. And that turns off the sort of like neurons that were going to promote the answer for, hey, I'm not, I'm not too sure. And so that's why the model answers in the Michael Jordan case, and that's why it doesn't answer by default in the Michael Batkin case. But what happens is if instead now you force the neurons for oh, this is a famous person to turn on even when the person is not famous, then the model is just going to answer the question. And in fact, what we found is in some hallucination cases, this is exactly what happens. It's that basically there's a separate part of the model's brain, essentially, that's sort of making the determination of, hey, do I know this person or not? And then that part can be wrong. And if it's wrong, the model's just going to go on and yammer about that person. And so it's almost you have like sort of like a split mechanism here, right? Where the model's like, well, I guess the part of my brain that's in charge of telling me I know says I know, so I'm just gonna go ahead and say stuff about this person. And that's at least in some cases how you get a hallucination.
Yeah, that's interesting because a person, right? So would go, do I know this person? Yes, I know this person. But then if you actually don't know this person, you have nothing more to say, right? Because basically, it's almost like you forget, okay, so I'm supposed to know Emmanuel, but I guess I don't have anything else to say.
Yeah, exactly. So I think the way I've thought about it is it's almost for us, there's definitely a part of my brain that feels similar to this thing where you might ask me, who was the actor in like the second movie of that series? And I know. I just can't quite recall it at the time. Like, they're this is how they look like. They were also in that other movie, but I can't think of the name. But the difference is if that happens, I'm gonna say, well, listen, Ben, I think I know, but at the moment, I just can't quite recall it. Whereas that's the part that like the models are like, I think I know, and so I guess I'm just gonna say stuff. And so that's that specific bit where it's not that the like, oh, I know or I don't know part is separate. That's not the problem. 'Cause I think we have something similar. It's that they don't. catch themselves sometimes early enough, like you would, where, you to your point exactly, you just be like, well, okay, I think I know who this is, but honestly, at this moment, I can't really tell you. So, let's move on.
By the way, this is part of a bigger kind of topic now in the AI space around reliability, right? So this notion of reliability and predictability. The idea being, I can have a model that's 95, 99% accurate, but if I don't know when the 5% or the 1% when it is inaccurate, if I don't know when that is, then it's quite scary, right? So I'd rather have a model that's 60% accurate, but I know exactly when that 60% is.
I mean, I think models are getting better at hallucinations exactly for that reason. That's sort of pretty important. People are training them to just be better calibrated, right? If you look at the rates of hallucinations for most models today, they're sort of much lower than basically the previous models. But yeah, I agree. And I think in a sense, there's maybe like there's a hard question there, which is at least in some of these examples that we looked at, it's not necessarily that, at least insofar as what we've seen, that you can clearly see just from looking at the inside of the model, oh, like the model is hallucinating. What we can see is the model thinks it knows who this person is, and then it's saying some stuff about this person. And so I think the key bit that, would be interesting to do future work on is then trying to understand, well, when it's saying things about people, when it's saying, this person won this championship or whatever, like, is there a way there that we can kind of tell whether those are real facts or those are sort of confabulated in a way? And I think that's still an active area of research, basically.
So in the case where you hook up Claude to web search,
Yeah.
then presumably there's some sort of citation trail where at least you can check, right? So the model is saying it knows Emmanuel and then says who Emmanuel is and gives me a link I can check, right?
Yeah, and in fact, I feel like it's even more fun than that sometimes. I had this experience yesterday where I was asking the model about some random detail, and it confidently said, "Well, this is how you do this thing." I was asking it how to change the time on a device. It's not important, and it was like, "This is how you do it." And then it did a web search, and it said, "Oh, actually, I was wrong. According to the search results, that's how you do it. The initial advice I give you was wrong." And so, yeah, I think grounding results in search is definitely helpful for hallucinations. Although, of course, then you have the other problem of making sure that the model doesn't trust sources that are unreliable, right? But it does help.
Case in point, science, right? So there's tons and tons of scientific papers now that get retracted. So just because it does a web search, what it should do is also cross verify that search with whatever database there is for retracted papers.
Right. And as you think about these things, I think you get in sort of like effort level questions where right now, there's if you go to Claude, there's sort of like a research mode where you can send it off on a quest and it'll do research for a long time. It'll cross-reference, tens and tens and tens of sources. But that will take, I don't know, it depends, sometimes 10 minutes, sometimes 20 minutes. And so there's a question of like, well, when you're asking about, I don't know, should I buy these running shoes? Maybe you don't care. When you're asking about something serious where you're going to make an important life decision, maybe you do. And so I always feel like, as the models get better, we also want them to get better at knowing when they should spend 10 seconds or 10 minutes on something.
Which, by the way, there's a surprisingly growing number of people who go to these models to ask health and medical questions. And anyone who uses these models know, a lot of it comes down to your prompt, right? So a neurosurgeon will prompt this model about brain surgery very differently than you and me, right?
Of course. Yeah. Well, and in fact, that was one of the cases that we studied actually, since, yeah, it has become, something that people use these models for, where we prompted the model with a case that's similar to one that, a doctor would see. So not sort of in the language that you or I would use, but, this sort of like, this patient is, age 35, presenting symptoms A, B, and C, because we wanted to try to understand how the model arrives to an answer. And so the question had all of these symptoms, and then we asked the model, well, based on all these symptoms, answer in only one word. What other test should we run? Just to force it to do all of its reasoning in its head. Can't write anything down. And what we found is that there's this sort of there were neurons that were activating for groups of neurons that were activating for each of the symptoms, and then there were two different groups of neurons that were activating for sort of two potential diagnoses, two potential diseases, and then those were promoting a specific test to run, which is sort of a practice in a differential diagnosis. The person either has A or B, and you want to run a test to know which one it is, and then the model, suggested the test that would sort of like help you decide between A and B. And I found that quite striking because I think, again, outside of the question of reliability for a second, there's like a depth of richness to just the internal representations of the model as it does all of this in one word, right? Where maybe think, oh gosh, okay, this makes me excited about continuing down this path of trying to understand the model. Like the model's done a full round of diagnosing someone and proposing something to sort of like help with the diagnostic, just in one forward pass in its head. As we use these models in a bunch of places, I sure really want to understand all of the complex behavior like this that happens in it in its weights.
In traditional software, we have debuggers and profilers. So, do you think as interpretability matures, our tools for building AI applications, we could have kind of the equivalent of debuggers that flag when a model is, I don't know, going off the rails?
Yeah, I mean, I that's the hope. I think debuggers are a good comparison actually, because debuggers mostly get used by the person building the application. It's not necessarily something, if I go to, I don't know, yeah, Claude AI or something, like I can't use really the debugger to like understand what's going on in the back end. And so that's the first state of debuggers is like, can the people building the models use it to understand the models better? And I think we're hoping that we're gonna get there at some point. We're making progress. I don't want to be too optimistic, but I think we're on a path here where this work that I've been describing, the vision was to build this big microscope, basically, where the model is doing something, it's answering a question, and you just want to look inside and look at just like a debugger will show you, basically the states of all of the variables in your program. We kind of want to see the state of all of the neurons in this model. It's like, okay, I definitely know this person neuron is on, and also the this person is a basketball player neuron is on. That's kind of interesting. How do they affect each other? Should they affect each other in that way? So I think in many ways we're sort of getting to something close where at least you can inspect the execution of your running program like you would with a debugger, right? You're inspecting the execution of the running model. Of course, then there's a question of what do you do with it? That I think is another active area of research where, if you spend some time looking at your debugger, you can say, okay, I get it. This variable, I initialized it the wrong way. Let me fix it. We're not there yet with models, right? Even if I tell you, well, this is exactly how this is happening and it's wrong, then the way that we make them again is we train them. So really, you have to think, like, can we give it other examples so they would learn to do that way? It's almost like we're doing, you know, neuroscience on a developing child or something, but then our only way to actually improve them is to change the curriculum of their school. So we have to translate from like what we saw in their brain to maybe they need like a little more math, or maybe they need a little more, English class. So, anyways, I think we're on that path. I'm pretty excited about it. We also open sourced the tools to do this a couple months back. And so, this is something that can now be run on open source models. And, people have been doing a bunch of experiments with them, trying to sort of like see if they behave the same way as some of the behaviors that we saw in the Claude models that we studied. And so I think that also is promising. And there's room for people to contribute if they want to.
Do you folks internally inside Anthropic have kind of special interpretability tools that not that the interpretability team uses, but now you can push out to other people in Anthropic as they're using these models? I don't know what these tools would be. It could be what you described, some sort of UX
Yeah.
or some sort of microscope towards the model.
I mean, right now we're still at the stage where sort of the interpretability team is doing most of the microscopic exploration. So this is really, and we're building all these tools and doing all this research, and it mostly happens on the team for now. I think there's a dream and a vision to have this. I think the debugger metaphor is really apt, right? But we're still in the early days.
So you used the example earlier, the part of the model that is a basketball player, right? So lights up. So
Yeah.
is that what you would call a concept? And from what I understand, you folks have a lot of these concepts. And by the way, so is a concept something that you have to consciously identify, or do you folks have an automatic way of here's a millions and millions of concepts that we've identified, and
Yes.
we don't have actual names for some of them yet.
That's right. That's right. So the latter one is the way to think about it. So the way that I like to describe it is basically, the model has a bunch of neurons. And for a second, let's just imagine that, we can make the comparison to, the human brain also has a bunch of neurons. And what we want to know is like, usually it's like groups of neurons that mean something. So it's like, if these five neurons are on, that means that, the model's reading text about basketball or something. And so we want to find all of these groups. And the way that we find them basically is in a automated, unsupervised way. And the way you can think about it in terms of how we try to understand what they mean is maybe the same way that you would do it in a human brain, where if I, had full access to your brain, I could record all of your neurons and I wanted to know where like the basketball neuron was. Probably what I would do is I would put you in front of a screen and I would play some basketball videos and I would see which part of your brain lights up. And then I would play some videos of football and I'd see hopefully, some common parts like the sports part and then the football part would be different. And then I play a video of like an apple and then it'd be a completely different part of your brain. And that's basically exactly what we do to understand what these concepts mean in Claude is we just run a bunch of text through and see which part of its weight matrices light up, of its activations light up. And that tells us, okay, this is the basketball concept, probably. The other way we can confirm that we're right is just we can then turn it off and see if Claude then stops talking about basketball, for example.
Do the nature of the neurons change between model generations or between types of models, reasoning, non-reasoning, multimodal, non-multimodal?
Yeah, I mean, at the base level, all of the weights of them all are different, so all of the
Yeah.
neurons are going to be different. So in the sort of like trivial answer to your question, yes, everything's changed.
Kind of like the brain, the basketball concept is close to the Michael Jordan concept.
Yeah, exactly. So I think that there's basically commonalities, and you see things like that. Like we don't at all have an in-depth understanding of the like anything that you'd have for the human brain. Where it's like this is the map of where the concepts are in the model. However, you do see that provided that the models are sort of trained on you know like they're all doing kind of the same being a helpful assistant stuff. They'll have similar concepts. They'll all have the basketball concept and they'll have like a concept for Michael Jordan. And these concepts will be they'll be using like similar groups of neurons. So there's like a lot of overlap between the basketball concept and the Michael Jordan concept in one model. You're going to see like similar overlap in most models.
So channeling your previous self, if I were to give you a keynote at a conference and I give you three slides, this is in front of developers, mind you, not ML researchers, right? So what are the 1 to 3 things about interpretability research that developers should know about or potentially even implement or do something about today?
Oh man, it's a good question. I think 3 slides. All right. And my first slide would say something like models, language models in particular, are complicated, interesting, and they can be understood. And it's worth spending time to understand them. The point here being, we don't have to treat them as this mysterious thing. We don't have to use approximate kind of, they're just, next token predictors or they're just sort of pattern
They're
matchers.
black boxes.
They're black boxes. We can look inside and we can make progress in understanding them and we can find a lot of rich structure. That would be slide one. Slide two would be the stuff that we talked about at the start of this conversation, which would be here's like 3 ways your intuitions are wrong. Oftentimes this is look at this example of the model planning many tokens ahead, not just predicting the next token. Look at this example of the model having these rich representations showing that it's sort of like actually doing multi-step reasoning in its weights rather than just kind of matching to some training data example. And then I don't know what my third example would be. Maybe this universal language example we talked about. So complicated and interesting stuff. And then three, what can you do about it? Um, that's the third slide. It's an early research area. There's not anything that you can sort of take, that will make anything that you're building better today. Hopefully that's if I'm giving this presentation in 6 months or a year, maybe this third slide is different. But for now, that's what it is. And so my encouragement would be, if you're interested about this stuff, there are, these open source libraries that let you do this tracing in open source models. And so just go grab some small open source model, ask it some weird question, and then just look inside its brain and see what happens. And I think the thing that maybe I respect the most and identify the most about just being a engineer or developer is just this willingness to understand, almost this stubbornness to understand. Your program has a bug, like I'm going to figure out what it is, and it doesn't matter what level of abstraction it's at. And I would encourage people to use that same level of kind of curiosity and tenacity to look inside these very weird models that are everywhere now. Those would be my three slides.
So let me ask a follow-up question. As you know, most teams are not going to be doing much pre-training. A lot of teams will do some form of post-training, whatever that might be, fine-tuning, some form of reinforcement learning for the more advanced teams. A lot of prompt engineering, prompt optimization, prompt tuning, some sort of context grounding like RAG or graph RAG. So based on what you know about more about how these models work than a lot of people, how would you approach these various kind of up, you know things in a toolbox for a team, right? So you got prompt engineering, some fine tuning, maybe distillation. I don't know. So put on your post training hat, and based on what you know about interpretability or how these models work, how would you go about systematically or in a principled way approaching post training?
Yeah. Lucky for you, I also used to work on the post training team at Anthropic, so I have some experience as well. Um, I think it's funny. I think that what I'm going to say is the same thing I would have said before I studied these model internals, but maybe I'll say it in a different way or something. Um, I think that the key takeaway I keep on having from looking at model internals is, God, there's a lot of complexity, and that means they're able to do very complex reasoning just in latent space inside their weights. There's a lot of processing that can happen more than I think most people have an intuition for. And two, that also means that usually they're doing a bunch of different. They're almost like doing three different algorithms at once for everything they do. So they're like solving problems like three different ways, and a lot of the times the weird mistakes you might see when you're looking at your fine tuning or just looking at the results of the model, it's like, well, there's three different ways to solve this thing, and the model just kind of picks the wrong one this time. So because these models are already so complicated, I find that the first thing to do is just pretty much always to build some sort of eval suite. I find that that's the thing that people fail at the most. You just, need to, even if it takes you, it doesn't take that long. It usually takes an afternoon. You just write down 100 examples of what you want and what you don't want. And then I find that you can get incredibly far by just prompt engineering and context engineering and just giving the model the right context. It's been my experience, yeah, I say this having worked on fine tuning models, that you kind of only want to resort to that if everything else fails. And then it's pretty rare that everything else fails, especially with the models getting better. And so, yeah, sort of like understanding that in principle, the models have an immense amount of capacity. And so it's just your job to sort of tease that capacity out is the first thing I would say. Or the second thing, I guess, after just build some evals.
And with that, thank you, Emmanuel.
Thanks, man.